We're diving deep into the geometry of AI architecture. Discover the hidden math that stops giant models from exploding during training. Welcome to our podcast, Artificial Intelligence. Papers and concepts curated by Dr. Satya Malik.
So we're jumping right into a topic where, the stability of these massive models isn't just an engineering problem. It's really a fundamental mathematical one.
It absolutely is.
And it feels like a very appropriate topic for us, considering that both my co-host and I are AI-generated models ourselves. We're sort of unpacking our own potential architecture here.
Exactly. We're looking under the hood.
Today, our mission is to unpack the DeepSeek AI paper, mHC Manifold-Constrained Hyperconnections. If you're out there training LLMs at scale, you know stability is it's everything.
The whole game.
So we really need to understand how this new paradigm solves a critical problem that, frankly, almost derailed its very powerful predecessor.
And to really get why MHC is such a breakthrough, we have to step back for a second. We need to start with the foundation of modern deep learning, which is the residual connection. Right, from ResNets back in 2016.
That's the one. Its success is all built on something called the identity mapping property.
That's the simple but really elegant idea that a signal from an early layer can travel directly to a much deeper layer without being changed.
Precisely. It's a preserved path, a direct highway through the network. In the equation, your output is just the original input signal plus whatever transformation the layer does. That simple addition conserves the signal.
And that's what keeps the model stable, even when it's hundreds of layers deep. It's the bedrock.
It is the bedrock we build on.
Okay, so let's talk about the architecture that tried to build on that bedrock, but ended up cracking the foundation. Hyperconnections, or HC, what was the goal there?
Well, HC was designed to get a performance boost without a huge increase in, the raw computation, FLOPs. And they did this in two main ways.
Okay.
First, they made the residual stream much, much wider. They expanded it from a base dimension of, say, c to n times c, where n is usually 4.
So they gave the signal a 4-lane highway instead of a single road. More room for features to mix and interact.
That's a perfect analogy. And second, they added 3 learnable mappings, HRES, HPRE, and HPOST 2, really mix up the connections within that new wider stream.
But one of those was the problem child, right? The HRES matrix.
That's the one. The HRES mapping was responsible for mixing features within the residual path itself, and that's where the risk was introduced.
So HRES looked good at first. It gave them performance gains, but then they tried to scale it. They started stacking these layers.
And that's when things went wrong. Because that HRES matrix was totally unconstrained, it just completely broke the identity mapping property we talked about earlier.
How so?
When you stack these layers, you end up with what's called a composite mapping. It's the cumulative product of all those individual HRES matrices, one from each layer, all multiplied together.
And since each one was just learning whatever it wanted, that final product, it must have spiraled out of control.
Exactly. The composite mapping just failed to preserve the average value of the features. This is, the textbook definition of numerical instability. The signal either vanishes or, much more often, it just explodes.
We're talking catastrophic failure during pre-training. And
Yeah.
the data they showed was pretty shocking.
It was. In their 27 billion parameter model, the HC architecture showed this sudden, massive loss surge around the 12,000th training step.
And it lined up perfectly with the gradient norm just going haywire.
It did. But this is where it gets really interesting, because when they quantified that instability, the number they got back is, well, it's terrifying.
This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
So they use a metric called Amax gain magnitude to measure how much the signal is amplified. For HEC, the peak amplification hit values of up to 3,000.
3,000. So the signal was, at times, 3,000 times larger than it should have been.
Yes. That's not just a training problem. It's a fundamental breakdown in the physics of the network. You simply cannot scale an architecture that does that.
Now, a 3,000x explosion is definitely a project killer. Okay, so that kind of disaster demands a real geometric solution. How did MHC restore stability while trying to keep the good parts of HEC?
The solution is all about geometric control. The whole idea behind manifold-constrained hyperconnections is to force that problematic HRES matrix onto a specific, well-behaved mathematical surface, a manifold.
So you're not letting it learn just anything. You're giving it very strict rules.
Extremely strict. By projecting it onto this manifold, you can mathematically guarantee that the signal propagation will be stable, no matter how deep the network gets.
And what is this magical manifold? What kind of geometry fixes a 3000x explosion?
They chose something called the Birkhoff polytope. And what that means, in practice, is that the H-res matrix is constrained to be doubly stochastic.
Doubly stochastic. That sounds like some kind of conservation law.
It basically is. For you listening at home, it means two simple things. All the numbers in the matrix have to be non-negative, and every single row and every single column has to add up to exactly 1.
Ah, so it's perfectly balanced. It ensures that when you process features, you're not just creating or destroying information out of nowhere.
It's an excellent way to think about it. It conserves the total weight of the system. And they enforce this during training using an iterative method called the Sinkhorn-Knopp algorithm.
Okay, that sounds computationally heavy, though. Running an iterative algorithm on every single pass?
Right.
Why not something simpler, like just clipping the values?
That's a great question, and it really gets to the heart of why this is so clever. They chose this specific constraint because it gives you 3 theoretical guarantees that simpler methods just can't provide. The extra computation buys you absolute certainty.
Let's walk through those guarantees then. What's the first one?
First is the geometric interpretation. A doubly stochastic matrix acts as a convex combination of the input features.
A weighted average, basically.
Exactly. And that mathematically guarantees that the overall signal level is conserved from one layer to the next. It directly fixes the problem that HC introduced.
Okay, that's a big one. What's number 2?
Number 2 is norm preservation. A known property of these matrices is that their spectral norm can't be greater than 1. That acts like a hard ceiling on signal growth, which directly stops the gradient explosion problem in its tracks.
And the third one must be what lets them stack these layers so deep.
That's right. Compositional closure. The set of doubly stochastic matrices is closed under multiplication. So if you multiply a bunch of them together, which is what the composite mapping does, the final result is also guaranteed to be doubly stochastic.
So stability is preserved across the entire depth of the model. It's not just a local fix, it's a global guarantee.
It is.
So let's bring it back to that terrifying number. If HCC had a peak gain of 3,000, what did mHC manage with this new constraint?
The difference is just profound. mHC brought that maximum gain down from 3,000 to a bounded maximum of about 1.6.
1.6? That's night and day. That's the difference between an architecture that can actually be scaled and one that is fundamentally broken.
It really is. This shows that your basic architectural choices, if you don't constrain them, can completely doom a project before you even start.
Okay, but achieving stability is only one part of the equation. We have to talk about efficiency. That wide design of HC created a huge memory I/O bottleneck, right? The memory wall.
It did, and this is where the engineering side of this paper is just as impressive as the math. The DeepSeek team knew if this fix was too slow, nobody would ever use it.
Right.
Their goal was to get all these benefits, including the Sinkhorn-Knopp algorithm, with only a marginal 6.7% additional time overhead in large-scale training.
Which seems almost impossible. How did they hide the cost of that geometric constraint so effectively?
They attacked the I/O problem from multiple angles. First up was kernel fusion.
Okay, so instead of the GPU doing one small operation, writing the result to memory, reading it back for the next small operation, and so on,
Which is incredibly inefficient. All that reading and writing is a bottleneck.
they instead bundle all those little steps into one big unified compute kernel. One read, one complex operation, one write.
That's the idea. It dramatically cuts down on memory bandwidth usage, which is, public enemy number 1 for training these huge models.
And what about the memory footprint itself? A 4x wider stream means 4x more activations to store.
For that, they used recomputing. It's a bit like gradient checkpointing. Instead of storing all those massive intermediate activations from the forward pass, they just throw them away.
And then recalculate them on the fly when they're needed for the backward pass.
Exactly. But they do it intelligently. They actually developed a formula to calculate the optimal block size to recompute, which minimizes the total memory usage. It's a very clever trade-off.
And finally, they had to deal with the communication between all the different GPUs in the training cluster.
Yes, overlapping communication. They extended a standard scheduling technique to make sure that the communication steps sending data between GPUs were happening at the same time as the computation steps. No one is sitting around waiting.
So after all that work, fixing the math, optimizing the code, what did the final results show? Did mHC deliver?
It absolutely did. In their 27B model tests, mHC completely stabilized training, got rid of those loss spikes, and ultimately achieved a final loss that was 0.021 lower than the strongest baseline.
And more importantly, it wasn't just a better number. The model actually got smarter.
That's the most critical result. On the downstream benchmarks, mHC didn't just beat the baseline, it surpassed the unstable HEC version, especially on reasoning tasks.
You mean things like BBH and DROP?
Precisely. We're talking gains of 2.1% on BBH and 2.3% on DROP. And those aren't simple tasks. They test complex multi-step reasoning. It's proof that a stable geometric foundation directly leads to more stable, more intelligent learning.
And these advantages held up as they scaled things even further.
They did. The scaling curves, both for compute and for tokens, show that the performance advantage is robust. It confirms that mHC is a truly scalable foundational building block for the next generation of LLMs.
So if you had to boil this all down, what's the big picture takeaway for people building these models?
I think mHC proves that macro architecture, the geometry of how layers connect, is just as important for scaling as the micro details of the attention mechanism. It gives us a powerful new tool to manage that fundamental trade-off between plasticity, a network's ability to learn, and stability, its ability to be trained at all.
It's a fascinating balance.
It is. And, the paper focused on doubly stochastic matrices because they guarantee stability.
Huh?
But the framework itself, the mHC framework, is more general. And that leads to a really provocative thought for the future.
Oh.
What other specific manifold constraints could we use? Maybe not just for stability, but for other goals. Could a different geometric constraint be tailored to improve, say, multimodal integration, or maybe make few-shot learning more effective? The geometry of deep learning is far from a solved problem.
A truly fascinating avenue for future research. And if these concepts of geometry and stability fascinate you, you really need to get the fundamentals right. I urge you to enroll in opencv.org/university to get started in computer vision and AI. Thank you so much for joining us for this deep dive into manifold-constrained hyperconnections. Be sure to subscribe so you catch the next one.